I'll just get you onto the bigger screen and try and get rid of that. Right, that's as big as we can get you.
Great.
Okay, you're good. Off you go.
After that interesting presentation, this is maybe not that much interesting, but this is presentation focused on the implementation of a hardware-rooted Bitstream security and secure manufacturing workflow using the PolarFire FPGAs and the Sundance PCIe 104N platform. The goal is to provide defense-grade protection for intellectual property and configuration data, not only in deployed system, but also through the manufacturing lifecycle. We will discuss the workflow, the role of all parties involved, the HSM-based security model, and how we integrate these elements into a real-world deployment scenario. I am going to walk you through the custom setup we built to ship program PCIe 104N board to a defense client. This board run on Microchip PolarFire FPGA, and we didn't pick that chip for its performance. We pick it because the security is actually baked into the silicon. We built our entire process around this hardware feature to make sure the hands-off from code to hardware is completely locked down. That way, the final product is fully tested and secure before it ever reaches the field. We can take this same workflow and plug it into any of other PolarFire boards we make, whether it is the Sun1, SE300, or something like Polar VPX. The process stayed the same. We design and build all of these boards right here in the USA. They come in different form factors to fit whatever project you are working on. But since they are all built around Microchip FPGA, we got the same secure provisioning and testing every time. The workflow we are working to explain here is all about ensuring the security of customer IP during every phase of manufacturing and programming. This ties directly baked into the US-made board I mentioned earlier. As you can see on the side, FPGA are becoming the top defense and aerospace FPGA because they are flexible and efficient. But the real headache is the deployment process. These boards move through a lot of different hands and locations, which creates some serious supply chain gaps. Because of these risks, we don't just look at security when the device is out in the field. We start at the point of manufacturing. By locking things down from the very beginning, we can guarantee the Bitstream stays exactly how it is supposed to be, and your IP stays private through the entire life cycle. The primary risk occurs before the system is even deployed. During manufacturing, testing, or programming, the Bitstream is potentially exposed to unauthorized parties. Without proper control, this would allow attackers to duplicate device, capture encryption key, or modify the configuration data. In defense application, such breaches are not acceptable, as they are compromise both security and mission reliability. Therefore, a comprehensive solution must be secure. The Bitstream across all stages of the life cycle. Modern defense systems face multiple attack vectors during the FPGA provisioning lifecycle. This includes intellectual property theft, hardware substitution, overbuilding of devices beyond the authorized quantity, interception or modification of Bitstream, and supply chain attack. Each of these represents a critical risk, as they could allow adversaries to create unauthorized copies of deployed devices or gain access to sensitive operational software, which would have severe security implications. One common threat scenario involved the insertion of a dummy FPGA into the programming chain. The attacker's goal is to capture encryption key when the device is programmed. While such device may mimic the electrical and timing behavior of a legitimate FPGA, they cannot produce the hardware root identity derived from the POF or the factory program key. This demonstrates the importance of robust authentication mechanism during the programming phase to prevent unauthorized access. To protect against this threat, several security requirements must be met. First, the FPGA must be uniquely identified to ensure authenticity. Second, the bitstream must remain confidential during transient and provisioning. Third, the device must be protected against cloning or duplication. Fourth, the life cycle of the cryptographic key must be tightly controlled. And finally, the manufacturing and provisioning operation must be disciplined and traceable, ensuring that security is maintained from assembly to the deployment. Our approach combines proven hardware security primitive, cryptographic mechanism, and controlled workflow. PolarFire FPGA provides hardware-rooted security features, while Microchip secure provisioning architecture support unauthorized programming. Sundance integrates these elements with a controlled production environment, applying process and procedural control to enforce secure manufacturing, testing, and provisioning. This ensures end-to-end protection without exposing sensitive key or bitstream to unauthorized parties. The secure provisioning ecosystem relies on three independent stakeholders: the customer, Sundance as the manufacturer, and secure test and programming center. Deliberately, each party has clearly defined roles that are separated. This intended separation of duties prevents any single entity from having full control over both the bitstream and the hardware, which is critical principle in defense-grade security architecture. In this workflow, the customer owns the intellectual property, generating the encryption key, and defines the production limits. Sundance manufactures the hardware while ensuring component origin, history, and integrity. The Secure Test Center performs validation and execute programming under controlled conditions. By assigning these roles, the architecture maintains strict boundaries and reduces the attack surface across the life cycle, ensuring that no single point of compromise exists. The customers serve as the root of trust. They generate the FPGA bitstream and user encryption key, UEK, in a secure environment and retain exclusive control over them. The customer also defines a number of devices allowed to be programmed, which prevent overbuilding. Because the customer can never leave the trusted environment, they maintain full ownership and authority over the intellectual property through the manufacturing and provisioning process. Sundance's role is to manufacture and assemble the PCIe 104 and board, according to the strict production and quality guidelines. We ensure that all components are sourced from trusted suppliers and maintain full traceability. While we provide hardware integrity and logistic control, we never access the customer key or Bitstream, which preserve their confidentiality. Our focus is on creating a trustworthy hardware platform for secure provisioning. The Secure Test and Programming Center acts as a controlled execution environment. It conducts functional and electrical validation of each board, ensuring the hardware operates correctly. The test center also executes the programming sequence using secure production programming framework, enforcing authentication and provisioning role. Importantly, it does not have access to the key in plain text, ensuring that sensitive cryptographic material remains protected. The workflow enforces a strict separation of trust domains. The customer retains control over keys and Bitstream. The manufacturer controls the hardware, and the test center executes provisioning under secure procedure. By enforcing these boundaries, we eliminate single point of failure and reduce risks. This zero trust approach is central to defense-grade hardware security and aligned with best practice, the secure supply chain management. Control and access are intentionally fragmented to prevent exposure to sensitive material. The customer alone handles cryptographic key generation and Bitstream creation. Sundance handles the physical board, and test center only execute predefined secure programming steps. This separation ensures that no party can unilaterally compromise either the hardware or the intellectual property. The end-to-end workflow spans multiple stages: manufacturing, testing, Bitstream creation, secure transfer, authentication, and programming. Each stage enforces a strict security control, ensuring that the FPGA configuration data remains protected at all times. By following these sequences, we maintain a controlled, auditable, and secure lifecycle for each deployed board. During the manufacturing, Sundance assembled the boards with trusted components and maintained full traceability of critical parts. Procedure ensured that no unauthorized components are introduced, and assembly occurs under controlled conditions. This foundation step reduced the risk of hardware tampering and established a secure This foundational step reduced the risk of hardware tampering and established a secure base for all subsequent provisioning and deployment steps. The boards are shipped to the secure test center where they undergo a strict electrical and functional testing. Verification includes power system, interface operation, and communication tasks to the FPGA. Only boards that pass all validation checks proceed to the programming phase. This ensures that only verified functioning hardware enter the provisioning workflow. The customer generates Bitstream and user encryption key entirely within a trusted, isolated environment, that is their customer environment. The user encryption key is applied to encrypt the Bitstream, ensuring that sensitive firmware remains confidential. Because this process occurs slowly under the customer control, key and intellectual property are never exposed to any third party, including the manufacturer or test center. The encrypted bitstream and user encryption key are securely transferred to the test center manufacturing HSM, hardware security module. We call it as HSM from now on. Transfer is performed using secure cryptographic protocol, ensuring that no plaintext key or bitstream data are exposed during transit. This control process guarantees confidentiality and provision an auditable trail of asset from customer to programming environment. Before provisioning, each FPGA is authenticated. The MHSM queries the device via JTAG, and the FPGA generates a PUF, physically unclonable function, derived the device ID. This ID, combined with factory programmed keys, is verified against a trusted signature. If the device fails authentication, provision is halted. This mechanism ensures that only genuine hardware receives the bitstream and keys. Once authenticated succeeded, the MHSM securely transferred the user encryption key to the FPGA, followed by encrypted bitstream. The FPGA performed internal decryption using AES 256 and stored the configuration securely. At no point is the key or bitstream accessible outside of the HSM controlled environment, preserving confidentiality and truth programming. The user encryption key is bound to the device using PUF-derived material within the FPGA. This ensures that the encryption key and bitstream cannot be reused on other devices, effectively eliminating the possibility of cloning. This finding enforces a hardware-rooted security model, which is essential for defense-grade applications. The number of device programs is strictly enforced by MHSM. When the predefined production count is reached, programming halts automatically. This prevents overbuilding and guarantees that only the authorized number of boards is deployed with the customer priority firmware. This control adds another layer of protection against supply chain attack. The customer maintains exclusive ownership of the user encryption key and bitstream through the workflow. Keys are generated and remain within the customer UHSM. This is user hardware security module, and they are never exposed to the manufacturer or test center. This strict ownership model, ensuring that control of intellectual property and cryptographic material remains fully in the hands of the customer. The system uses a two-tier HSM model to ensure separation of responsibility. The customer HSM, that is the UHSM, generate and encrypt the key and bitstream, while the manufacturing HSM, MHSM, handle device authentication and provisioning. This division ensures that sensitive operation and data are never exposed to unauthorized parties. The UHSM relies entirely within the customer's secure environment. It generates the user encryption key, encrypt the bitstream, and define the production limits. This HSM serves as root of trust for provisioning workflow and guarantees that cryptographic assets are never exposed outside of the customer control boundaries. The HSM at the test center executes the provisioning process. It validates the FPGA device, enforces production limit, and programs the device using encrypted assets. Importantly, it cannot generate keys or decrypt the bitstream, ensuring that sensitive cryptographic material remains under customer control while enabling secure programming. The interaction between the UHSM and MHSM provides a control mechanism for secure provisioning. The customer encrypts and transfers the asset. The HSM validates the device and enforces the provisioning workflow. And the FPGA receives the key and bitstream only after successful authentication. This structure exchange enforces securely and accountability. This architecture guarantees that no key are exposed, devices are authenticated, production limits are enforced, and all operations are auditable. By combining hardware-rooted identity, cryptographic controls, and process discipline, the system provides end-to-end security across the entire provisioning lifecycle. Qualifier FPGA provide the hardware root of trust. They include factory programmed keys and physically unclonable functions that generate a unique device identity. These hardware mechanisms prevent duplication, impersonation, and unauthorized access, forming the foundation of the secure workflow. A physically unclonable function using macroscopic silicon variation to produce a unique device-specific response. These characteristics are impossible to replicate, which means that every FPGA can be uniquely identified based on its inherent hardware properties. The device identity is derived from the TOF and factory keys. It is not stored in a memory that regenerates when required. This identity is used to authenticate the FPGA before any provisioning occurs, ensuring that only legitimate devices receive the encrypted bitstream and user encryption keys. A dummy or counterfeit FPGA can't reproduce the correct POF-derived identity or validate signature. If authentication fails, provisioning is halted immediately, preventing key exposure. This mechanism effectively neutralizes attempts at hardware impersonation during programming. Bitstreams are encrypted using AES 256 in content and authenticated with HSA 256. This ensures both confidentiality and integrity. Even if the encrypted bitstream were intercepted, it would be useless without the user encryption key, which remains securely bound to the intended FPGA. Qualifier FPGA include built-in differential power analysis, DPA resistance. During decryption, key material is altered after each block to remain a statistical pattern that could be exploited. This protects the UEK from side channel attacks that attempts to extract key from power consumption signature. The workflow aligned with recognized cryptographic standards, including AES 256 and HSA 256, adhering to these standards, ensuring interoperability, regulatory compliance, and robust cryptographic assurance for defense application. Effective security requires a system-level approach, hardware-rooted identity, controlled provisioning, workflow, and separation of responsibilities. Qualifier provides primitive security features, while Sundance integrates them into a disciplined production and programming process. This layered approach ensures protection against cloning, overbuilding, and supply chain attack. This presentation demonstrated a scalable, defense-grade solution for securing FPGA bitstream from manufacturing to deployment. By combining hardware-rooted identity, authenticated encryption, HSM control provision, and a strict separation of responsibility, the workflow provides comprehensive protection for intellectual property and operational security. Thank you for your attention. If you have any question, I'm here to answer.
Any questions from the room? Stunned into silence, end of the day.
Okay.
I don't know if there's any online. I can't see them on the screen. Let's put the chat up. Nothing online, I think. No, that's not. And that's it. Wasn't it? The last one. Yeah. Okay. So thank